Welcome back everyone to our calc series. Today we'll be talking about monotonicity and critical points. Now, I want to introduce the idea of monotonicity first. And what this says is basically whenever your f prime is greater than 0, f of x is increasing. This is a very simple idea, right? So if you have something like this, for this interval, this first part, you would have that f prime x is greater than 0. This is because the function is increasing, and whenever you take 2 points and try to get the derivative, it will be positive, right? And it is increasing. So whenever you have f prime x is greater than 0, f of x is increasing. And here we have f prime x is less than 0. So it's f prime x is less than 0, forcing the function to go down. So this is something very key, but fairly obvious. Then we can use this to determine places in a function that are increasing or decreasing. So we're first going to go and practice this. So for example, here we can define this to be f of x, and we can take its derivative. So here we would have a product rule. Oops. And we can factor. Now, this is increasing whenever it's positive, as we noted. So when does f prime of x when is f prime of x greater than 0? That is when e to the x, x plus 4, x minus 2 is greater than 0. And we notice e to the x is always greater than 0. And this is greater than 0. This is solving a quadratic inequality, and we would find that x is less than negative 4, or x is greater than 2. So this is when it is increasing. Now, it would be decreasing when f prime of x is less than 0. So you could do the same work, and you would find that x here, would have to be between negative 4 and 2, like this. So this is for increasing, this is for decreasing. Okay, sweet. Now we can do the exact same thing. Here we have cosine x, and we consider when this is greater than 0 and less than 0. So we see it is greater than cosine x is greater than 0 when x is in negative pi over 2 to pi over 2. I'm just going a little faster here. This is when it's positive or increasing. It's decreasing when x is in negative pi to negative pi over 2, union pi over 2 pi. Of course, this is set notation. You could also stick with what I just wrote here. You could go x is between this or x is between this. They're essentially the same thing. Here you can do the same. So f prime of x is equal to 12x squared minus 6. This is greater than 0. This is greater than 0 whenever x is greater than 1 over root 2, or x is less than 1 over root 2. And if x is in between, then we have decreasing. Right, like this. This one we'll leave as an exercise for you. Now, having covered this, we know how to determine monotonicity, and now we're going to introduce critical points. A critical point on f exists if and only if that point has derivative 0 or does not exist. Now, the whole point of finding these critical points, why are they called critical, is because they are candidate points. Candidate points for local extrema. So we would notice that all the points that are local extrema have to be critical points, except endpoints. So you could have endpoints, there are exceptions, but over the internal interval, all the critical or all the local extrema are critical points. So you have to have all the real set of all candidates, you would have critical points, and you would have endpoints. So these are the two parts of candidates. So endpoints is fairly easy. Usually you're given an interval, but critical points is the harder part to find, which is exactly when f prime c is 0 or f prime c does not exist. So now let me illustrate to you why these are all the points that we consider for local extrema. So for example, let's say we have something like this. We notice that for this part, it's monotonically increasing. So f prime is greater than 0 for this interval. But then f prime of x is less than 0 for this interval. And we notice that there must be this point at the top here must have f prime x equals 0, because it serves as like the transition point from increasing to decreasing. And if you have increasing before you and decreasing after you, this must be the local maximum, right? So not only the first part of finding local extremum is to have critical points, and then you also need to analyze the behavior around it, which is exactly what the first derivative test does. But the first derivative test is the process of finding all points with f prime equal to 0 or does not exist, and then analyzing the behavior of its neighbors. So for does not exist, I can illustrate something like this, right? This is what we call a cusp. And we see at this point the derivative does not exist. They're both positive infinity. One of them is positive and one of them is negative infinity. And this is a local maximum though. So like these undefined points could be very special like this, and so we examine these two. Right. So as for practice, let's consider this right over here. So one classic thing that we could draw is a derivative sign chart or graph. So we consider f prime, and we have these points -4 and 2. So we see we've analyzed previously that over the interval over x less than 4 or -4, the derivative is positive. So the function is increasing, and at greater than 2, it's also increasing, and here it's negative. So we have f prime positive, negative, positive, and at -4 and 2, we have 0. So these are our critical points. So we are trying to find critical points are -4, 2. And for each of them, we consider their neighbors. So for -4, we're going to go like, okay, if I'm less than -4, if x is less than -4, it is increasing. For x greater than -4, it is decreasing. So at x equals -4, I would be hitting a maximum, because before I was increasing, now I'm decreasing. So this is a local minimum. At x equals 2, for x less than 2, we have decreasing. For x greater than 2, we have increasing. Then this would be a local maximum, right? And are these all our local extrema? Yes, because there are no endpoints. So we've considered all the critical points, and these are these two. Right. So let's do one more right over here. We can draw the same sort of chart. Notice here we do have endpoints, but it's open, which means these endpoints are not included, and you can't really get to a specific endpoint. So there's no way we can have an endpoint extrema here, an extremum here. So here our chart would look something like this. Positive, negative, negative. And we would hit 0 here. So easily decreasing, increasing, this is a local minimum, and this is a local maximum. So we have these 2 points. So with more practice, you should be able to identify these points more and more quickly. So just a reminder, all local extrema are critical points or endpoints. So consider these 2 categories and check for each. So this is a summary. Yeah, this is a very nice summary of what we've been doing. So if we look at this chart right over here, we see that 2 and 4, we have local maxima. So in both cases here, the pattern is that before it, the derivative is positive, and after it, the derivative is negative, and they are both critical points. Here we have f prime is equal to 0, and here we have f prime is undefined. So we have one of each, essentially. And both of them would give local maximums because the sign changes from positive to negative. At x equals 3 and x equals 5, and x equals, oh, okay, we don't have another one. But at x equals 3, we have derivative goes from negative to positive, and it is f prime equals 0, like this. So this would be a local minimum. Oops, minimum. At x equals c1 and c5, we see no extremum. So this is an extreme in a case that we haven't considered yet. So when we have a critical point, not all critical points are extrema. This is important. So here, for example, we have f prime is equal to 0. It is a critical point. But before it's increasing, after it's still increasing, it's just like taking a pause, then it would be neither a minimum or a maximum. All right. So this is these two are cases where not all CP are extrema. So neither or nor. Ooh. For endpoints here, very special. We look at basically the one side that exists around it. So for example, here for the left hand endpoint, if the right hand is increasing, then it's a minimum. If the right hand is decreasing, then it is a maximum. Say we can apply the very same reasoning here. As we already did for 1, 2, and we already did this for 1, 2 here. So I'm just gonna do one more for this one. I'm gonna scroll back up and just do one more here just to show you. So here, a standard way to do this now is, let me write down all the steps. 1, identify the critical points. So let me illustrate that here. So here, we do this by first finding f prime of x. So f prime of x is 12x squared minus 6, and f prime x now needs to be equal to 0. 0 happens when x equals plus minus 1 over root 2. Is it possible, and then you consider if it's possible for this to be undefined, and it's not. So these are our only critical points. And then for each of them, it's very convenient if you have a sign chart like this, right? So you could draw a sign chart and analyze the signs of this. This is very convenient because the positives and negatives are perfectly separated by the points where you have 0, or the critical points. So here you could draw something like this, and you go like plus, minus, minus. And at these points you have 0. And then you can go like, when x is less than negative 1/2, 1 over root 2, you have f prime x is less than 0. When x is greater than 1 over root 2, negative 1 over root 2, f of x is greater than 0. So this would be x equals negative 1 over root 2 is local minimum. Minimum is a local minimum. And you could do the same thing, same reasoning for x, for 1 over root 2, like this. So this is the second step. And then third of all, don't forget the endpoints. Do at least take a look at them. Here there are no endpoints, you would see. This is defined over an entire domain, all real numbers, and so you don't really have endpoints. So here are our only 2 local extrema. So these are the 3 steps. Identify critical points, look at the neighborhoods, and then look at endpoints. 3 steps for finding local extrema. Right, and I think that is it for today's video. Thank you.